Okay, so the title of my talk this morning, Application of Cathodic Protection to Offshore Wind Turbine Monopiles. And this is just a quick summary of some work that's been undertaken at the Intertek labs, I suppose pretty much over the last 10 years or so. I've been involved myself, but also others, other colleagues, Gareth John, Jim Stott, and Petra Ernst. So there's four areas that I'm going to just briefly run through, particularly the first two, just a quick overview of cathodic protection to give you some background, and then look at some issues that arose on the application of external galvanic anode systems to some of the early monopiles. And then to look internally, the space inside the monopile, which is filled with seawater, to look at the application of galvanic anodes there. That's a retrofit activity. And then protection into narrow gaps. So cathodic protection, what is it? Well, the aim of it is to promote the cathodic reaction, to reduce the corrosion rates so that materials like carbon steel can be used successfully in fairly corrosive seawater conditions. The potential of the steel is reduced and an alkaline environment, a passive environment generated at the surface. When the only reaction on the metal surface is the cathodic reaction, then corrosion is suppressed and the system will be viewed as protected. And potential criteria are used to assess whether protection has been achieved. And so just a quick schematic to show you. Focusing on the galvanic systems here, rather than the impressed current type of cathodic protection, you're basically attaching a galvanic anode that is consumed and provides ionic current and electrons and protects the structure. You're pulling the potential of the steel down to more negative values. And if we look at a sort of microscopic level, there's small corrosion cells that will be active on the steel surface, anode areas where corrosion is taking place, and cathode areas that support that the reaction. And then when you've applied cathodic protection, you're looking more at this situation where the anode activity is shifted to the galvanic anode, and the corrosion on the steel surface is shut down and the steel is protected. And there's, of course, the electrochemical reactions occurring, the anodic reaction, the dissolution of steel, iron 2+ being formed. And if we're talking about anodes, of course, zinc or aluminium will be going to their respective ions. And then on the cathodic side, the reduction of oxygen is the main cathodic reaction, and that produces the alkaline environment, the OH. There are alternative cathodic reactions, the evolution of hydrogen and water reduction as well. So on some of the early monopiles, there were some issues with with external protection, and these have been addressed in the latest DNV standard that's been issued. And this covers all the zones, the corrosion zones. So we've got the atmospheric condition at the top, but then for cathodic protection, of course, we're looking at the splash zone and then the submerged zone and the section buried in the seabed. May need some protection. And it's in internal and external areas that need to be considered. So the new standard mandates that CP is required for the external surfaces, and an optional protective coating is suggested. As I say, there have been some cases historically of some poor performance, and this was largely due to three factors. the insufficient design current density that was allowed for in the calculations, and then also interactions between the anodes. There's limited space for installation and attenuation down the length of the monopile. So just looking at the issue with design current density, the wind turbines are typically located in shallow waters and quite close to the shore. There's a tendency there for perhaps higher levels of oxygen in the more aerated water, and also increased flow, tidal conditions. And both of these factors led to a current density higher than the standard values that were being applied. And so the revised standard includes a 50% uplift on those standard values, so quite a considerable increase. This, of course, has knock-on effects in terms of anode life and the amount of material that's required. The second issue that came up was anode interference. And when galvanic anodes are located close together and there's limited space on the monopile, on the transition piece, for the installation of the anodes, obviously they need to be kept below low water. When they're located very close together, there's interaction effects between the anodes. This is known about and can be calculated, but it decreases the anode output. So in combination with the increased current density that's needed, if there's then a reduction in the amount of current that could be supplied, insufficient current was being provided. And one other aspect that affects the current output from galvanic anodes, the resistivity of the environment. And again, in coastal areas, the seawater may have some dilution from the rivers, the runoff from the estuaries, and so you've got lower salinity, which leads to a higher anode resistance and reduced current. So again, this issue has been addressed in the latest standard, and it recommends detailed analysis by computer modelling if you're going to, if you're concerned about anode location being too close. It's also suggested, the application of a coating. If you can, particularly during the initial period, if you can reduce the amount of current that is required, then you're able to develop a stable and protective calcareous deposit on the surface, which improves the long-term performance. And then the final issue that was that came up. This isn't an ideal arrangement of anodes. If they're located in one small area on the structure, it would be better to have anodes located along the length of the monopile. But for installation reasons, it's much easier to connect them onto the transition piece and install them after the foundation has been put in place. But that can lead to then poor current distribution, let's say down at the greater depths where the current has further to get to. But if a coating is applied, then you improve the current distribution and are far more likely to get protection to the base of the foundation. So I want to go on and talk about two laboratory studies that were undertaken at Intertek to look at issues that arose within internal protection. And the first was associated with retrofit CP to some some monopiles. The strategy for control of corrosion internally was initially based on stagnant seawater conditions, so a stifling of corrosion due to the main cathodic reaction, oxygen being limited, and then that would lead to a long-term low corrosivity inside. But unfortunately, this didn't necessarily work in all cases for several reasons. Leaking water seals, so there are cables that enter through a port in the monopile. If those seals fail, then you've got possible water exchange. There's also that the seabed may not be completely watertight. If it's a permeable seabed, then as the tide goes up and down, there'll be some water exchange coming through the seabed. And then on the atmospheric side, inside the monopile, there's a supposedly internal airtight deck, which is supposed to seal above the water level, but that's not always airtight. I've heard people say you can hear it whistling as air goes in and out. And you've got, of course, you have to have an opening, hatch opening for personnel to get down to carry out maintenance work. And each time that's open, then you will let in fresh oxygen. So because there were some issues, it was decided to install some aluminium anodes on the inside of a series of monopiles to prevent corrosion inside after the failure of the seals. Retrofit aluminium anodes were installed, but it wasn't successful in some cases, and it wasn't initially understood why this was happening. And it was found that the pH was dropping significantly. So the pH of seawater is typically around neutral, pH 8 or so. And this dropped within a few weeks to around pH 4, so quite an acidification. And it was associated with the aluminium anodes dissolving in the seawater and generating the aluminium ions, which were then hydrating, and this is a reversible reaction, but creating acid within the enclosed environment. And we were appointed to carry out some laboratory testing to investigate this issue. And so, as a starter, as a benchtop activity, some aluminium chloride. This was to simulate aluminium dissolution. Aluminium chloride was added to just some synthetic seawater, and the pH recorded. It was left to stand and stabilize for 10 to 15 minutes. And for comparison, the test was repeated with zinc chloride, and the results confirmed what had been seen in practice, that there was, with the addition of aluminium, the blue line here, there was a significant drop-off to around pH 4, whereas you'll note with the zinc in the up here, there was limited reduction, still above pH or around pH 7. And so we then moved on to look at setting up some simulations to try and simulate what had happened in practice, this acidification that had been seen. And the aim was to try and keep the certain ratios and as similar as possible to a full monopile. So we were looking at the anode and cathode area, the cathode area to seawater volume, and the geometric arrangement of the test. And so these, in the end, we used some large plastic pipes which were set up and filled with seawater to represent the monopile. We set tests up with both aluminium and zinc anodes for comparison, and a steel coupon represented the monopile, and that was a vertical strip set up inside the test cells. And we had ports for various measurements at the top, in the middle, and lower down for measurement of potential and current, and also we had the ability to measure pH and undertake water sample analysis. We're able to remove small amounts of water during the test. And so just a brief summary of some of the results. So in the lab benchtop tests, we'd seen that the zinc didn't create an acidification problem, and that's again shown here on the right-hand side. So sorry, I'm jumping ahead a little bit. This first set of results are the ion concentrations. So we can see that in both cases, with time, it's about 2 to 3 weeks there, we saw development of aluminium and zinc in the solution, which of course is what you would expect. Here's the pH results, and on the zinc side, you can see that during the test period here, the values are remaining around 7 to 8, whereas for the aluminium, again, we saw a sharp reduction after only a couple of weeks, and then it was fairly stable at about pH 5 after that. So we were also, as I say, monitoring the CP, the potential and current, and on here you can see, if we look at the zinc side, that the current there is shown in green, and we're seeing a drop-off in the current with time, and that's expected as a calcareous deposit forms on the surface. The current density requirements drop down. During the test, we did interrupt the test here at these dates, shown by the dashed line, to throttle back the current by inserting a resistor, because we were concerned about generating too much corrosion. But the main difference is, although we didn't see very high current in the aluminium test, it's considerably more than the zinc side, and that's the effect of the lower pH. So the test was successful. We got the stable calcareous deposit that we were expecting. We did see that the aluminium anodes created a reduced pH, but the zinc results were far better, and so zinc would be recommended for any other further retrofit applications. And then just briefly then on the cathodic protection into narrow gaps. This is the seal down here, which was failing, and there was concern as to whether the metal surface within the cut hole was protected or not. And so we set up some tests to look at whether the cathodic protection could get into this very narrow gap. There was limited information within the literature to cover cathodic protection into gaps where there was a flowing environment. That was the key difference. Some calculations were undertaken, and they showed that there was variability because, of course, uncertainty in some of the inputs there. But we were seeing the possibility of under protection. And so, again, a lab simulation was carried out. It's quite a complex test piece. This was a 3D printed arrangement. and we used a number of different widths, 1, 3, and 7 millimeters, and passed natural seawater through the gap at different flow rates. And what we saw from the results was if there was no flow, so let me skip on to this one, the results here. If there was no flow, we got satisfactory protection in almost all cases, just the very most, the narrowest gap, and if protection was only installed externally, you didn't then get protection as the gap. But if you had protection internally and externally, then the criteria was met. And in flowing conditions, it was harder. There were several instances there. Where internal protection wasn't applied, then there was insufficient protection in all three of the gaps that we looked at under a variety of flow rates. And that can be seen here in this plot here, these plots here, where the protection level is we're looking for more negative than -800, so all these points up here are underprotected, whereas within the when external and internal protection is applied, then all values were more negative than 800. So just to wrap up then, in stagnant conditions, protection was only could be achieved in all cases except for the 1 millimeter gap. Protection was less likely to be achieved in the flowing environments. We saw that in the test results. That was quite clear. And to get protection, you need to apply externally and internally cathodic protection. And to summarise the overall the work, in the past years, the application of cathodic protection was not always successful. The new standard addresses many of the issues that came up, so now the new designs will be more robust. Internally, where corrosion control strategies failed, it's best not to use aluminium anodes because they can cause seawater acidification if the exchange of seawater isn't sufficient. Zinc is a much better option. And where seals are leaking, you will probably get satisfactory protection into the gap as long as good protection is applied both internally and externally. So thank you. Thank you for your attention, and any questions, if there's time.
Any questions?
Really interesting talk.
Thank you.
I'm really interested in the internal acidification issue because in a closed system, the pH should always go up because the generation of alkalinity on the cathode is more efficient than the hydrolysis reaction at the anode. So it's interesting to see that you saw magnesium hydroxide being formed at the cathode. Is the precipitation of that the reason that the overall pH goes down instead of up?
Certainly there's alkalinity generated at the surface that causes the scaling. I would say that yes, that may be the main reason. We were reliably seeing the acidification in the bulk, and I think it was we didn't investigate further into the actual more detailed electrochemical reactions and the balance, but I think you're probably right, yeah.
Any other questions?
David, I just wondered what percentage of these inshore wind turbines have been affected by these issues in terms of the overall?
Yeah, that's a good question. It was a fairly small number. But of course, with it being offshore structures, it was creating quite a lot of concern. It was in the earlier days. And of course, quite a lot of expense to go out there and retrofit. Of course, not all wind turbines have this particular monopile structure. Those with jacket structures wouldn't be affected by this. So it was a small fraction, but I'm afraid I don't know the total number.